Theorem number 2 is property 2 on eigenvalues. If lambda is an eigenvalue of A corresponding to eigenvector x, capital X, then lambda power n is an eigenvalue of A power n corresponding to eigenvector x. Means if lambda is the eigenvalue of A, then you have to show that lambda power n is also eigenvalue of A power n. You have to prove like that. Means this theorem we can prove by mathematical induction. Already you know very well mathematical induction theorem. Now first, given lambda is an eigenvalue corresponding to eigenvector x, that implies Ax equal to lambda x. Already suppose if x is an eigenvector of A corresponding to eigenvalue lambda, the formula is A minus lambda I into x equal to 0. From that one only we are calculating eigenvector. Means if lambda is an eigenvalue corresponding to eigenvector x, means the equation compulsory we will get the formula Ax equal to lambda x. This is equation number 1. Basic definition. Pre-multiplying with A on both sides, that implies A into Ax equals to A into lambda x. A into A is, that implies A square x equals to lambda is parameter, you can write outside, again in bracket Ax, lambda into equation 1 Ax equal to lambda x, again I am writing here lambda into lambda x, it becomes A square x equal to lambda square x. The theorem is true for n equal to 2. Now directly A power k into x equal to lambda power k x, means this is the, let the theorem be true for n equal to k. Now pre-multiplying with A on both sides for the above equation, A into A power k into x equal to A into lambda power k into x, A power k plus 1 into x, then lambda power k is parameter, you can write outside in bracket Ax. Now you can send A inside. Lambda power k into Ax is nothing but lambda x, this implies lambda power k plus 1 into x. The theorem is true for n equal to k plus 1. By mathematical induction, if lambda is eigenvalue of A, then lambda power n is eigenvalue of A power n. Means we have proved by mathematical induction. Theorem number 3 is property on eigenvalue, third property. If lambda is an eigenvalue of A is non-singular corresponding to eigenvector x, then lambda inverse is also eigenvalue of A inverse corresponding to eigenvector x. Nothing is there. If lambda is the eigenvalue of A, then you have to show that lambda inverse is eigenvalue of A inverse. Lambda inverse means 1 by lambda, or lambda inverse is an eigenvalue of A inverse. Given that basic definition, lambda is an eigenvalue of A corresponding to eigenvector x such that Ax equal to lambda x, equation number 1, and A is non-singular matrix. That implies non-singular means determinant of A not equal to 0. Pre-multiplying with A inverse on both sides, A inverse into Ax equal to A inverse into lambda x. A inverse into A in one bracket x equals to, from associative property actually this is, lambda is parameter outside, A inverse into x. A inverse into A equal to I into x equal to lambda into A inverse x. Then A inverse x equal to, I am writing RHS part, you can send lambda that side, 1 by lambda into x, because I into x equal to x. Therefore, it is in the form of Ax equal to lambda x, instead of A inverse is there, here instead of lambda 1 by lambda is there, means if Ax equal to lambda x, then lambda is the eigenvalue of A. Then A inverse into x equal to 1 by lambda into x is nothing but 1 by lambda is the eigenvalue of A inverse. Therefore, 1 by lambda is the eigenvalue of A inverse. Theorem number 4, property 4 on eigenvalue. If lambda is an eigenvalue of non-singular A, then determinant of A by lambda is an eigenvalue of the matrix adjoint A. If lambda is the eigenvalue of A, then determinant of A by lambda is also eigenvalue of matrix adjoint A. You have to prove like that. Given lambda is an eigenvalue of non-singular matrix A corresponding to eigenvector x, such that Ax equal to lambda x. This is equation number 1. From basic definition we are taking this equation. Now pre-multiplying with adjoint A on both sides. Pre-multiplying with adjoint A on both sides. Then adjoint A into Ax equal to adjoint A into lambda x. Then RHS side, lambda is parameter, you can write outside adjoint A into x. Then adjoint A into A equal to determinant of A. Determinant of A into x. Then you can send lambda this side, determinant of A by lambda into x equal to adjoint A into x. Now A into x equal to lambda into x, then lambda is the eigenvalue of A. Then adjoint A into x equal to determinant of A by lambda x means A by determinant of A by lambda is an eigenvalue of adjoint A. Once again, Ax equal to lambda x. If you have this equation, lambda is an eigenvalue of A. Then in the same way, here the last equation, observe the last equation, adjoint A into x equal to determinant of A by lambda into x, means determinant of A by lambda is an eigenvalue of adjoint A. Therefore, determinant of A by lambda is an eigenvalue of adjoint A. Theorem number 5 or property on eigenvalue, property 5 on eigenvalue. This is very important. Many times I asked this property. Eigenvalues of a Hermitian matrix are real numbers. Means if they have given Hermitian matrix, then if you are calculating the eigenvalues of that matrix, then purely real numbers, no complex numbers. Now Hermitian matrix means they will give one matrix, any square matrix. For that matrix, you do the transpose of that matrix. Again, take the conjugate of each and every element. Then we will get the matrix A only. Then this type of matrix is called Hermitian matrix. Means capital A equal to Aij is said to be Hermitian matrix. Then Aij equal to Aji whole bar is nothing but Hermitian matrix. Later we will discuss the how to solve the eigenvalues of the Hermitian matrix. Now proof for this matrix, let A be the Hermitian matrix, lambda is the eigenvalue of A corresponding to eigenvector x such that Ax equal to lambda x. This is the basic definition. Pre-multiplying with x power theta on both sides. X power theta is nothing but conjugate transpose. A power theta is nothing but A bar whole transpose. X power theta is nothing but x bar whole transpose. Instead of x bar transpose, I am writing here x power theta on both sides. X power theta into Ax equal to x power theta into lambda x. Taking conjugate transpose on both sides. This is equation number 2. Above equation is equation number 2. For this 2, taking conjugate transpose on both sides, then x power theta Ax whole to the power of theta, x power theta lambda x whole power theta. Means A power theta equal to A bar whole transpose or A power theta equal to A transpose whole bar, that can be written as, and A B C whole to the power of theta equal to C power theta, B power theta, A power theta we are writing here. X power theta, A power theta, X power theta whole to the power of theta, that can be written as, this is nothing but A power theta, lambda power theta is nothing but lambda bar here, X power theta, again x power theta whole to the power of theta. Once again I am repeating here, this lambda is parameter, lambda power theta is nothing but lambda bar, this x power theta, last one, again x power theta whole to the power of theta. Then LHS side, A power theta is A because A is Hermitian matrix, right? A power theta is A. Now x power theta, A power theta is nothing but A into x equal to lambda bar x power theta into x. From 2 and 3, observe this one, x power theta into Ax can be written as, in the equation number 2, x power theta into Ax equal to lambda x power theta x. Lambda x power theta x, I am writing that part. Lambda bar into x power theta x. Then you can send this side, lambda minus lambda bar into x power theta into x equal to 0. Since x is non-zero vector every time, x power theta into x is not equal to 0, means this part is not equal to 0, means definitely lambda minus lambda bar equal to 0. Therefore, lambda equal to lambda bar means conjugation of lambda equal to lambda only. Conjugation of 7 bar equal to 7 means purely 7 is real number. Conjugation of I is minus I, like that. Observe that one, I is complex number, conjugation of I is minus I. That's why here lambda equal to lambda bar, it indicates lambda is real number. Therefore, eigenvalues of Hermitian matrix are real numbers. This is very important.